So in this section, we're going to go through how to graph something in 3 dimensions in a 2-dimensional surface. So one thing that you are going to have to be comfortable with is knowing your basic shapes, like what does a parabola look like, what does an ellipse look like, or a hyperbola. Those are going to be pretty common shapes you're going to see over and over here. So refresh back on those if you need to. It's just going to be ones through the origin, though. If we did anything else, it would make that way too complicated. So the way we're actually going to go about graphing these is instead of trying to just jump right into it, you can't plot points like you would in 2 dimensions. So what we're going to do is we're going to see instead, if I look at what's happening just in the XY plane or the XZ plane, what does the graph look like there? And then can I combine all of these different shapes to get that 3-dimensional surface? So here, in order to graph a surface, or in order to sketch the graph of the surface, it's useful to determine the curves of intersection of the surface with the coordinate planes. So kind of like when we talked about the projections of a point, if you were standing on the y-axis and looking in the direction of the xz plane, you're seeing what does that point look like there. We're essentially doing the same thing here. If I stand on the y-axis and I look in the direction of the xz plane, so I'm basically looking perpendicular to it, what does the shape look like in that 2-dimensional space? Instead of calling that projections, though, we called them traces of the surface. So these curves are called traces of the surface. So we're going to look into a bunch of common shapes, but I'm going to start by just giving you a random one. So we're going to go through a bunch of different surfaces that involve all of our variables x, y, and z. But what I'm going to do is I'm going to start with one that's missing one of those. So the example we're going to begin with is sketch the surface of z equals y squared in R3. Okay. So I'm missing an x variable here. So that tells me really my x is completely free. It can be whatever value I want. So if I'm finding points that satisfy this equation, x can be any number, but then my y and z are restricted to this equation. So if you think of z equals y squared, that's just the shape of a parabola. But because x is free, I'm basically going to take that parabola and move it along the x-axis. So here, there are no x's in the equation. So really what that means is on any plane where x is equal to some constant or a number, that's parallel to the YZ plane. The trace on that would be a parabola. So essentially what we're doing is we're taking the parabola that's in the YZ plane and we're moving it along the x-axis. Okay. All right. So let's go ahead and draw this to the best of our abilities. Now, one thing I am going to do is I'm going to kind of copy and paste this axis that I'm doing because we're going to need this a ton. So I want to draw the negative x-axis, the negative y-axis, and the negative z-axis as well. So we're getting a real good photo here. And then this is a little long, so let's go ahead and shrink that down. Okay. So I am going to use this a ton. So just for my own sake, we're going to move a copy of that off to the side so I can just copy and paste it for the other problems. So what happens here is if I did not have my x-axis, here is my YZ plane, I'm going to go ahead and I'm going to graph the parabola here. And we're going to do that in yellow. So I'm going to make this dotted, but z equals y squared is just a parabola. Now, if I go ahead and I add that third dimension back, okay, what I'm essentially doing is I'm taking this parabola, and because x is free, I'm dragging it forward and backward along the x-axis. And what that's doing is it's creating kind of like a half pipe, and it's infinite in each direction. So specifically, this is the line z equals y squared, where x is equal to 0. And now that's being dragged forward and backward. So to get that full shape, we've got the parabola in the front, and then we've got the parabola that's in the back, which I'm going to do as dotted. And then we're going ahead and we're connecting the dots. So it's creating a half pipe of infinite length. Okay. So it's going to be very, very difficult when you're starting out drawing these surfaces. But I cannot also stress enough how important it is for you to be able to draw these by hand. Yes, you can use online softwares and you can get a really good 3D image here. However, you cannot use an online software on your exams. So you're not going to have a 3D graphing calculator for it. You need to be able to draw this surface to then figure out other key details. Okay. So this is our shape for this particular surface. If I had a similar equation, say y equals x squared, all that means is you graph the parabola in the xy plane and you drag it along the z. So it's a lot of symmetry. So what happens here, because it's got this parabola shape, but I'm moving it along the x-axis, we call this a parabolic cylinder. So what we're going to do now is we're going to look at a bunch of our different surfaces that involve all three of our variables. So each of them is going to have their own specific name, but in general, we have something to describe just this classification of surfaces. Because realistically, you're not going to be able to sketch the surface like ln of xy. That's going to be very difficult for you to go through. So these are just ones that have nice shapes that are broken down based on our general circles, ellipses, hyperbolas instead. So these are called quadric surfaces. So for our definition, a quadric surface is a graph of a second degree equation in three variables. So if you remember, we talked about like quadratic equations. That was just x squared or y squared, something of that. It gave you a parabola. Technically, ellipses were like x squared plus y squared equals some constant, or divided by something. Those were all technically quadratic because they had second degree at most on the variables. Same idea here. So a quadric surface is a graph of a second degree equation in three variables. Specifically, those variables are x, y, and z. The most general of these equations is going to look horrendous. So the most general such equation is the following. You're going to have some constant times your x squared, a different constant, potentially, times y squared, and then something times z squared. And then technically you can have cross variables. So you can have something times xy, something times yz, something times xz. Then you can have each variable times a constant. And then you can have a constant at the end. And so this equaling 0 is our most general form for a quadric surface. So this is where A through J are constants. Okay. You haven't seen anything with these cross sections, but what you have seen is if I ignore all of this, you've seen equations of this form because the values in front of the x's and y's could be positive or they could be negative. These would give you those different surfaces of circles, ellipses, and hyperbolas. So now when we're adding the z component, it would basically be adding those two things. What these three terms in the middle do is allow for rotation. So all of our shapes can be rotated on different axes, so they're pointing kind of in a different direction. We're honestly just going to ignore that because it would make life way, 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 way too difficult. So instead, under translation and rotation, that's what these do. These translate it along the x, y, and z axis. Remember, it moves your center point for a circle or an ellipse or a hyperbola. We're going to reduce this down to something that's way simpler. So, however, under translation and rotation, we can reduce this to two equations. And these are the ones we're going to be working with. So we can have a constant times x squared, a constant times y squared, a constant times z squared, and ignoring all of these, which translate and rotate it, you're just going to have some constant equals 0. Okay. Another possibility, though, is ignoring this component, because if you think back to parabolas, you need just z as a single variable like we had back up here. You need something without a square term. So ignoring the x squared component or z squared component, ignoring all of the translations and rotations, we end up with another equation. Not ignoring that iz, we need that single variable. And then that j is just going to move things up or down, so we're going to ignore that too. So our two equations are going to be of this form. Okay. And then realistically with this one, it could be, instead of just z being the one that has the single power, it could be x with a single power and the z is squared. It's all going to be very similar. It just kind of tells you which axis this points in the direction of. Just like if you consider the difference between y equals x squared and then x equals y squared. Both parabolas, one opens along the x-axis, one opens along the y-axis. So they're very, very, very similar to each other. So really all I have in this section is we're going to do a bunch of sketching the surfaces, and then we're going to go ahead what the name of that is going to look like. So for our first one, we're going to sketch the surface. Which is 4x squared plus 4y squared plus z squared equals 16. So before I even start trying to sketch these things, I want to figure out the traces in all of my different coordinate planes. So I'm going to start by seeing what is the xy trace. And so what that means here is if I'm in the xy plane, remember your z is going to equal 0. So all I'm going to do is I'm going to set this component equal to 0. And what's left over is the equation 4x squared plus 4y squared equals 16. And dividing by 4 to make this nicer, this is x squared plus y squared equals 4. So this is our first trace of what's going on in the xy plane. This is a circle, which has radius equal to 2. So I'll know that shape in the xy plane. Now we're going to move on to the yz trace. And if I'm in the yz plane, that means x is equal to 0. So all I'm doing in this case is setting this piece equal to 0. So that gives us 4y squared plus z squared equals 16. And here, because I have a different constant in front of the y and the z, this isn't going to be a circle. Instead, it's going to be an ellipse. And for an ellipse, I always want 1 on this side, because remember, the component underneath tells me how much to move in each direction. So dividing by 16 gives us y squared over 4 plus z squared over 16 equals 1. So this is an ellipse. Like I said, you want to be comfortable graphing these, but just to kind of show you here, if you were to graph this thing, here is the y and the z. Your center is at the origin because it's y minus 0, z minus 0. So your center point is right here. This value of 4 tells you you're going to move 2 from the center in the y direction. So the endpoints here would be 2 and 2, and I need to move that a little closer. So here's 2 and here's 2. So the endpoints are this. 16 being under z tells you you move 4 in the z direction. So it's always the square root. So you would go up here to 4 and down here to -4. And that gives you your shape of that ellipse. Okay. All right. Then we got one more trace left, which is the xz trace. and then we can combine these all together to one graph. So if I have the xz trace, y is missing, so we set y equal to 0 in our equation. So that gives us 4x squared plus z squared equals 16. And you really end up with a very similar ellipse. So with these 3 different traces, I can then go ahead and draw my 3D graph. So again, I'm going to go back up here because I made a very nice picture to start with. And I just want to go ahead and keep using the same thing. And put it right here. Okay. So we're going to start with our XY trace. It is a circle of radius 2. That means I need to go 2 in every direction. So I'm going to go ahead and do my best to keep this consistent. We go 2 in each direction. And then if you notice in the Z, I need to go a distance of 4. So I'm going to go ahead and do 4, just while I'm at it, marking everything up. Okay. So if I want to do my XY trace, that means I'm ignoring my Z and I'm drawing that graph in this XY plane. So it's going to make sense for me to just copy 2 of these to make life easier. So I'm going to need to draw those back in. So in the XY plane, I have a circle. The center is at the origin, and then I go a distance of 2 in every direction. So it's not going to look quite like a circle because, again, it's a distorted perception. But I'm going to go ahead and connect the dots. Anything that's in this front, I'm going to draw as a solid line. And then anything in the back, I'm going to do dotted to just make life simpler. Because otherwise, I'm going to have a ton of solid lines going on. So this is the equation x squared plus y squared equals 4. And our z is equal to 0. Now I can go ahead and add my z-axis back in. And now I'm going to do my yz trace. So if I'm doing the yz trace, I do not care about the x-axis. And I'm going to graph this shape in my resulting coordinate plane. So here, you again work with the center at the origin. In the y direction, I'm going to go a distance of 2. And in the z direction, I go a distance of 4. And because this is that flat plane, I can go ahead and draw everything here as a solid line. So this is my ellipse. Not super smooth, but again, it's okay. You're drawing it by hand. So this is the equation y squared over 4 plus z squared over 16 equals 1. Now I can add my x-axis back in. Let's shorten it a little so this way it's not running into that. And then last but not least, I've got to go ahead and draw this last equation, which ignores the y-axis. So I'm going to go ahead and get rid of that. And in this distorted again perception, I'm going to go ahead and draw an ellipse. Center is at the origin. In the x direction, I go a distance of 2. And then in the y direction, I go a distance of 4. And then I'm getting an ellipse that is on this angle that I'm looking at. So this is the front of the ellipse, and then we'll do a dotted to draw the back. And now we can go ahead and add the y-axis back in. and I have my three-dimensional image of this ellipse, okay, or this surface. So the nice thing though, to kind of just give you an idea of our future, if you go ahead and you slice this ellipse at any plane parallel to the XY axis, that image that's on there is always going to be a circle. If you go ahead and slice this sideways, it's always going to be an ellipse. And then likewise, if you slice it parallel to the YZ plane, it's still going to be an ellipse. So this is basically when you're setting x equal to some constant, and then you're getting a different ellipse from here. Okay. So this kind of shape also has a name. Now I'm going to get rid of this and move it to my next spot because we're going to need it down there. And then I'll come back up. So this is called an ellipsoid. So the equation of this is just a rearrangement of what you see up here. You're going to have x squared divided by some constant, y squared divided by a potentially different constant, and then z squared divided by a potentially different constant. And you're going to need the square root of that, which is why we write a squared b squared c squared underneath to indicate how far you're moving in each direction. Okay. All right, so that is our first shape. Again, take your sweet time drawing these while you're starting out. Do not just use an online software. Draw these by hand. So let's move on to our next surface. Same directions, honestly, for all of these. Sketch the surface. So I'm not going to bother writing that each time. Surface we're going to look at now is z equals x squared plus y squared. So I'm going to start again by going through our traces. We've got the xy trace. We've got the yz trace. And then we've got the xz trace. Most of the time, just knowing these three is enough to get a picture. This is one case, though, you're going to see we run into a bit of a problem here. So if I go to find the xy trace, that means z is going to equal 0. If I plug that into the equation, that gives me 0 equals x squared plus y squared. Technically, that is a circle centered at 0, 0 with radius 0. So there is really only a single point that this gives us. So all this xy trace does is it tells me that I go through the origin, which great, that's nice, but that's a point. That doesn't help me graph in 3D. So what I'm going to need is a different trace for a different z value. Z equaling 0 did not provide us anything super useful. So we'll do that at the end. Now for the other traces, at least those are nice. So for the yz trace, x is equal to 0. So we just get z equals y squared. Okay. So this is a single point. And then this shape here is going to be a parabola. Then if we move on to the xz trace, it's very similar. We just get z equals x squared. So in turn, we get another parabola to graph. Now, because z equals 0 was useless to us, what I'm going to do is I'm going to let z equal a different constant. You can try 1 to start, and it should be enough information for you. If 1 doesn't work, then try -1 or try 2. You're going to see I'm going to pick some kind of funky ones just to show you because I know what these shapes look like. I know what value z is going to give me something easy to work with. So if I set z equal to 1, that will give me 1 equals x squared plus y squared. And this is something I can use. I know what this looks like. So this is a circle of radius 1. Okay. So the reason that I needed this is since the xy trace was useless, we're going to let z equal a different number to find another trace. Okay. And you're also going to see, although we harped on you way long ago about making sure that you labeled all of your axes with numbers really nicely, that is not as important here as opposed to the overall shape. Okay. So again, I'm going to need this thing, and I need 2 versions of it. But my y cut off. So here's y. Okay. So if I start with the xy trace, that's boring. I just know it goes through the origin. So I have that single point here. Now going through the yz trace, we ignore the x axis, and I'm going to draw a parabola in this direction. Because it's z equals y squared, that tells me it opens in the z direction. Okay. And now we can go ahead and we can add the x-axis back in. Okay. Now moving on to the xz trace, we ignore y. And again, I'm going to get a parabola, but it's got to open in the z direction. So I'm getting kind of a sideways parabola here. Here's the front of it, and then I've got the back of the parabola here. So this is z equals x squared. Might be easier to honestly just do this. There we go. So adding those axes back in, now I'm going to go ahead and I'm going to do the trace when z equals 1. So basically what that means is I'm going to see if I take this plane z equals 1, which I'll say is right here, here's 1. Along this plane, I'm going to have a circle of radius 1. So if I slice this shape on this plane, I'm going to have a circle as that intersection. Okay. So when z equals 1, I'm going to have a circle of radius 1. So this trace here is x squared plus y squared equals 1, z equals 1. So now I can add the top of this in just so you can see it, but honestly you can leave it like that. But what happens is if I were to pick z equals a different number, I would still get a circle as that cross section here. Okay. So this is going to be the shape of this surface. So again, now I don't need this. Let's go ahead and just move this out of the way. Oh, I didn't mean to duplicate it. I meant to just move it, but that's fine. We'll just erase this. Okay. So the name of this is going, because it involves technically ellipses, because circles are a special case of an ellipse, and a bunch of parabolas. This is called an elliptic paraboloid. So specifically, this one is z is our variable that has 1 power with some constant, and x and y are the ones that are squared. But realistically, it could be any of the variables that have a single single exponent, not a square. All that does is it changes the way in which this opens. So you can see z is the variable that has a single exponent. It opens in the positive z-axis. If it was negative z, it would open in this direction. If instead it was x equals z squared plus y squared over whatever constants, then it would open in the x direction. And then if it was y, all it means is it opens along the y-axis. So same exact shape, but just different orientations. Okay. All right, so let's try our next shape. Again, same directions. We're going to do z squared equals x squared plus y squared. And we're going to restrict this to our z being non-negative. Okay. So you can see z squared's off on its own. Again, same kind of shape is going to happen if x was on the left-hand side or y was. It's just going to have a different orientation. So we'll start by seeing are the normal coordinate plane traces enough. And if not, then we got to do more work. Okay, so if we start with the xy trace, again, we get 0 equals x squared plus y squared. So this is boring because it is a single point. So that tells me I'm going to need to pick a different z value to get a trace. If I do the yz, that gives me z squared is equal to y squared. Now that shape I don't know. However, if I go ahead and I take the square root, remember because you take a square root, you technically get plus or minus. So instead of these two just canceling out, you actually get the absolute value of y. If you don't do that, you'd end up with z equals y, which is just a single line, and that doesn't work out for us. And again, this is because our z value, we're told, is non-negative. Okay, so we're only getting that positive case here. Okay. So this is our second trace. Let's move this to the bottom so it's not interfering with the xz trace. And then this really is likewise, you get z squared equals x squared. When you take a square root, technically you get plus or minus the absolute value. But because we said z is positive, we go ahead and put the absolute values around this. All right. So we've got two good traces, but again, because this one was useless, it's just a point, you pick z to be another number. Again, you can pick z equals 1, that works out. Let's pick a different one just to show you, you still end up with the same thing. If I pick z to be 2, that gives me 2 squared is x squared plus y squared. This is just a circle of radius 2. If you pick z to be 1, it would be 1 squared equals x squared plus y squared, a circle of radius 1. If I pick z to be 4, it's 4 squared equals x squared plus y squared. That is a circle of radius 4 then. So it really makes no difference what constant you pick. You have that freedom. Just try something and see, does it give you something nice as a shape you can graph. Okay. So now that we got everything, let's go ahead and graph this. Okay. So we've got circles. We can go ahead and give us some marks to kind of see. Specifically, just because I'm letting z equal 2, I'm going to go up to 2 here. And then the others we'll just do our best. So the first one was useless to us. It was the point through the origin. Now, if I do my YZ trace, We ignore the x value, and I have an absolute value function. So remember, the shape of that is just going to dissect these directly in half. And this would be the equation z equals the absolute value of y. Now, putting that back in, let's go ahead and do the y's or xz trace. So we ignore y. And again here, I'm going to have the absolute value, which dissects these in half. So harder to do. And let's go ahead and graph the back of this. So this one is z equals the absolute value of x. Now we put those back in, and now I'm graphing z equals 2, which is a flat plane. So along this plane, I'm going to have a circle of radius 2. That's centered here at that point where z equals 2. So if I were to cross this, it's giving me a circle. So this is z equals 2. And we get the equation x squared plus y squared equals 4. Again, if I picked a different value here just to show you, if I picked z to be 1, you would still get a circle of radius 1. So that means if I slice this at z equals 1, I still get a circle. Okay. So that gives us our overall shape. And hopefully you can kind of recognize what this looks like. It's kind of like the bottom of a snow cone. And since that cross section of this thing, no matter where I cut it, you're getting a circle in this case. Really, the more general case is you could get an ellipse as that cross section. So this is called an elliptic cone. So hopefully the names make sense. In this one, you had a bunch of parabolas. The cross sections, when you cut them, were ellipses or circles. Here, no matter the way you slice and dice this, as long as it's parallel to one of the coordinate planes, you're getting an ellipse. So it's an ellipsoid. This one is just called a cylinder because it's something that's moving forward and backwards. And it's parabolic because it's a parabola. Okay. So hopefully those names make sense. But in this case, an elliptic cone, you have one variable off to the side, and then the others combined together. And whatever variable is on its own is the direction that it opens up in. So if this was x squared equals something involving z squared plus y squared, that means the cone would open in this direction instead. So a lot of just symmetry going on. So we've got 3 more special shapes left. What we have not seen from our basic graphs are hyperbolas. And so that's going to be in these last 2 shapes, or last 3 shapes. So same directions, sketch the surface, and we're looking at x squared plus y squared minus z squared is 1. So the minus, again, is just going to be the indication of the orientation, which way it opens up. Okay. So let's find our traces. Let's do the xy trace, yz, and then the xc. You don't have to write trace either. You can just write xy, yz, xc. Perfectly fine by me. So starting with the xy trace, when we set z equal to 0, this is nice. We get x squared plus y squared equals 1. So this is a circle of radius 1. Moving on to the yz, that gives us y squared minus z squared equals 1. So if you remember the shape of this, this is a hyperbola. And to just give you that quick refresher on a hyperbola, we're dealing with yz. The numbers underneath the y and z tell you the direction that it moves out in. So because the numbers under each of these are 1, that's great. Our center is at 0, 0. Because y is positive, that tells me it's going to open in the y direction. And because it's a 1 under y squared, that tells me that I move 1 in each direction. And then we have our hyperbola shape. You can get more precise because you can find the asymptotes, but again, we're just going to do this not super intricate. Okay, so I have that basic idea. So this is a hyperbola, and it opens along the y-axis. Okay. And then likewise, if you do the xz trace, you get the same thing, but the x squared is positive. So this also gives us a hyperbola. Specifically opening in the x direction. Okay. Now technically, because you have a trace in each of these, it is enough. So I'm going to draw each of these and kind of show you why it might be useful to also find some other traces. So we can get a really good picture from this though. Okay. So here, starting with our xy trace, we ignore the z-axis and we have a circle of radius 1. So here is the front of our circle. Make that as nice or as even as I possibly can. And then we've got the back of our circle. And it is a circle of radius 1. So that is 1 in every direction. Now moving to the YZ trace, ignore the X values. And we have a hyperbola that opens in Y's direction. Because this is a 1 underneath, it tells you you move 1 in the Y direction. And then I open so that my parabolas are gripping the Y-axis. So it looks something like this. And now let me label each of these because I did not do this. This is y squared minus z squared equals 1. And then this right here is x squared plus y squared equals 1. Now we've got our xz trace, so we ignore the y-axis. And again, I should be hugging, or my parabola should be hugging the x-axis. So moving 1 in each direction still puts me at the endpoints of that circle. And you can see this is why it's a little strange. We've got the piece in the front, and then we've got the hyperbola in the back. Okay. So it kind of looks like a tree branch, or like if you remember drawing trees as a kid, it's like it's this shape, but 3-dimensional. So you've got that base being bigger, and then the top of the tree gets bigger too. Okay. So this is our graph. Now let's move this out of the way because I gotta label this thing, but also because I want to show you that I'm going to pick some other values of z to kind of see what these cross sections look like. It seems like if I were to cut it, I get circles at those intersections, but just to verify. So what I'm going to do is I'm going to pick 2 different values of z. I'm going to start by picking a positive value. So we'll let z equal 2. In this case, that would give us x squared plus y squared minus 2 squared equals 1. So that gives me minus 4. Moving that over gives us x squared plus y squared equals 5. So this is a circle. It just has a funky radius of √5. That's okay. That means if I were to slice this thing at z equals 2, I get a circle as the top. So this allows me to just kind of get a complete picture going on. Then if I do the same thing and I pick a negative value of z to see what the bottom looks like, we'll do the same thing but -2. When you take -2 and square it, it's still going to give you 4. So you really end up with a symmetric shape. So you get a circle at the bottom as well. So that means down here, this shape is a circle. So again, it just gives you a more complete picture when you're going ahead and drawing the top and bottom of this as well. So the shape, what you can kind of see is it involves hyperbolas. So this is going to be something called a hyperboloid. Now we have two different types of hyperboloids. There's hyperboloids of one sheet and hyperboloids of two sheet. Basically, because you can wrap this thing with a single sheet of paper, this is called a hyperboloid of one sheet. And so here this is x squared over some number, y squared over some number, and z is the one that is negative. If it was x that was negative, it would just be this thing rotated and opening in this direction instead. If y was negative, it's along the y-axis. Okay? All right, so that's our hyperboloid of one sheet. Now let's do the hyperboloid of two sheets. And basically, you can think of, because this is one sheet, you had one negative sign. Two sheets, you're going to have two negative signs. So for our next figure, we're going to sketch z squared minus x squared minus y squared equals 1. So starting with our traces, I'm not going to write the word trace anymore because we've written it so many times now. Okay. For the xy trace, if I let z equals 0, this gives me negative x squared minus y squared equals 1. Well, maybe I think this is a circle because I have x squared and y squared and they're the same sign. However, if you multiply everything by -1, it gives you x squared plus y squared equals a negative number. A positive number plus a positive number equaling a negative number is not possible. This has no real solution. So basically that means there is no x and y value that will solve this equation if z equals 0. So ultimately, because this shape doesn't exist, this means there's nothing going on in the xy plane. So again, it provides us some useful information, but it's kind of useless for the actual graphing. So I'm going to have to pick some different values of z other than 0 to see if I get something that works out. And then I made these a little bit too close, so we got to move these over. Now going through our yz trace, that will give us z squared minus y squared equals 1. And that's great. That is a hyperbola. The only difference is if here is the yz plane, because z is positive, we open in the z direction. So it's a hyperbola that opens in z. Then we've got our xz, which is similar. It's z squared minus x squared equals 1. So this is a hyperbola as well. That also opens in Z. Now I need to pick some other values for Z since 0 was useless. And again, you can start by saying Z equals 1. But because I already know what this looks like, I'm going to kind of pick funky looking numbers because it just makes life easy. So if you do try to pick Z equals 1, that would give you 1 minus x squared minus y squared equals 1. Moving that to the other side gives us 0 over here. So really you end up with x squared plus y squared equals 0. So this ultimately just gives you a point. It goes through 0, 0, 1. So not very useful. So if I pick -1, it would be the same thing. So let's try the next number. Let's do 2. If I pick Z to be 2, this will be 4 minus x squared minus y squared equals 1. And then just rearranging it, if I move the 1 to this side, that's 3. Moving the x squared and y squared over, you get a circle. It's just a funky radius of root 3. So if you want something that's super duper nice, I will tell you, you could pick Z to be the square root of 5. Because then Z squared is 5. And what that does is it makes it so you have 4, and then you have x squared plus y squared over here. So it gives you a nice circle with a nice radius. So our circle of radius 2. And then realistically, if you plugged in negative, because this is Z squared, it turns it to positive root 5. So you really get 2 different pieces directly from this. So we've got our different traces. So this way I ignore this line that's here. Let's move everything to a fresh page. Because again, I know this is difficult when you're first starting out, so I want to keep this as clean as I possibly can. Okay. So starting with our YZ trace, let's get rid of the x-axis. We have a parabola, and I know 1 and -1 are going to be important. Again, I'm not going to bother labeling these, but just to show you for that instance, it moves up and down a distance of 1. And then we need to hug the z-axis. So I have one parabola opening here, and then another parabola opening here. Now, going through the xz, we ignore y, and again, we have a parabola. So let's first label this. This is z squared minus y squared equals 1. Now moving on to the next one, it's still a parabola. It moves up and down a distance of 1, and then I open in the z direction. So here's the back of that hyperbola. Sorry if I just said parabola instead of hyperbola. So that is z squared minus x squared equals 1. And then we have those two different traces. If I were to cut this off at z equals root 5, then when it intersects with these curves, it is forming a circle. So ultimately what that means is you have a circle connecting these. So this specific one would be, yeah, I can leave that there. Z is equal to positive root 5, and then you have x squared plus y squared equals 4. And then to just clean this up, let's go ahead and get rid of this piece here, and then connect the dots for the back there. If you do the bottom, same thing. When you slice this at z equals 5, you get a circle. So you get a shape that looks like this. So it does have nice symmetry. And again, clean this up. Let's go ahead and get rid of these. So this would be z equals negative root 5, and then x squared plus y squared equals 4. So this is our other shape. You can see you would technically need one sheet to wrap this like a present. You need another sheet to wrap this as a present. And then if I were to cut this with different planes that are going to be parallel to the xz or yz, you're going to get a bunch of hyperbolas as intersections. So it is going to be called a hyperboloid, and because you need two sheets to wrap this present, it is a hyperboloid of two sheets. So the equation for this will be one thing is positive and the other two are negative. Okay. And the positive just tells you which direction it opens. So this is along the z-axis. If it was x squared, it would be those same shapes, but along the x-axis. So we got one last fun shape here. Let's go to a new page for this one too. This is probably the most interesting of the shapes, at least I think. And it's going to be seemingly nice, but it's kind of a complicated picture. Okay, so we've got z squared, or z equals y squared minus x squared. So going through our traces, let's see what we get. So if I do the xy trace, this gives me 0 is equal to y squared minus x squared. Moving the x squared over and just putting y squared first, this is the same as y squared equals x squared. Taking a square root, remember you get a plus or minus. And then when I take a square root of something squared, it doesn't just cancel, it gives you the absolute value. So ultimately what that would mean is in the xy plane, you're really going to have two absolute values, one being positive, one being negative. It gives you a giant cross. So yes, this can be useful for us, but in this particular example, that's a lot going on. I'm going to try some other traces instead because it's not going to give me a full picture. This is the one weird example. So this unfortunately is not going to be super helpful. And you'll see just when we try to draw it, it will muddle our picture a ton. Now the other traces will be useful. So the yz is z equals y squared. That is a parabola. The xz trace is z equals negative x squared, which is a parabola that's just pointing downward. Okay. So what I'm going to do is I'm going to start by graphing these two things and to show you why we're going to need more information because of this one not being super helpful for us. So let's start with the YZ trace. Oh, no, that's not the eraser. Ignoring that gives us Z equals Y squared, so we have a parabola. Then if I add the x-axis back in, looking through the xz trace gives us z is equal to negative x squared. So that is a parabola that's going downward. So I'm going to draw this as dotted. Don't want a giant chunk of a solid line there. Okay. Now you can see if I go ahead and try to do this xy trace, I've got an absolute value pointing in each direction. And I have no idea what that does to the shape because this is real funky going on. So unfortunately, these lines going in this direction don't help me because what happens if I slice it this way? What does the graph look like? If I slice it this way, what does my graph look like? I can't tell based on these pieces. So what I want to do is I instead want to find some other traces. So again, I'm going to pick the same thing. I'm going to pick some nice values of z and see, do I get something that I can draw easily? So we'll start with if I set z equal to 1. So going back up here, this gives me 1 is equal to y squared minus x squared. That shape I know, this is a hyperbola. And this opens in y. So if I slice this at z equals 1, which is a plane like this, I have a hyperbola opening along the y-axis. So what that means is you have a hyperbola in this direction. And if I pick z to be a different constant, it would be the same thing. So essentially, if I slice it along this direction, you're going to see a bunch of hyperbolas that look like this. Okay. So that helps me out a little bit. Now let's try another value of z. Let's pick z to be negative 1. So plugging that in gives me negative 1 is equal to y squared minus x squared. Well, kind of looks like a hyperbola still, but let's go ahead and multiply by negative 1. So it just switches the direction of these. So this is also a hyperbola, but it's opening in the x direction instead. And now I no longer need this thing, so we're doing good. So if I were to cut this at z equals negative 1, I'm still going to get a hyperbola on that plane as a trace, but now it's opening in the x direction. So what we're actually getting here is we've got a hyperbola this way, and then we've got the back of the hyperbola over here. Okay. This is one of the funkiest shapes we're going to have. You might not be able to see it super well, but what it actually forms is kind of like a saddle. If you ever look up the image of a saddle of a horse, you have the front coming upwards so that you have the grip to hold on to, and then it has to go down the side of the horse as well. So we tend to call this a saddle. Okay? So kind of just connecting the dots so you can see this thing. We'll connect this top parabola to this one. This would go back and connect over here. And then the front, we've got these two pieces. And then in the back, we've got these two going on. So it is a very funky shape. Like I said, this is definitely the most difficult to draw, but it is the most interesting shape for us. This specifically is called a hyperbolic paraboloid. Because its cross sections are either going to be hyperbolas or parabolas. So the format for this is z over c is equal to x squared over a squared minus y squared over b squared. Okay. So again, very, very, very difficult shape to draw. We're going to kind of use this for an example later on, but this actual surface isn't going to be essential that you know how to draw it like thoroughly. The other ones, however, are going to be shapes when we start talking about double integrals and triple integrals and volumes and things of that nature. You're going to see them way more frequently than this shape. But this will be useful for us and when we talk about optimization or maxes and mins. Because this point in the middle is going to be interesting because it's going up in one direction, but down in a different direction. And just to kind of show you this with a nicer visual, Desmos has a really good graphing calculator that you can use that's completely free. Again, do not just plug your picture into here and get the shape and go through your homework. It's really important for you to graph these by hand. So instead, do them by hand first and then utilize a calculator to help you out. So with this shape, what we had is z is equal to y squared plus or minus x squared. So you can see you get something real funky here. So let's see if I can rotate this around. So you get kind of a saddle looking shape. You can see that middle. In one direction it's opening upwards, in one direction it's opening downwards, and you can see those absolute value functions in here. So that's our z-axis, that's our x-axis, and then depending on just where you rotate it, you've got the hyperbolas pointing in each different direction. So it's a hyperboloid or hyperbolic paraboloid, but you can also consider this like a saddle. So get lots of practice with graphing these. Again, take your time and do it by hand. You need to know how to do this in 2 dimensions. Because when we get to the chapter on vector calculus, it is important that you know how to graph these and know what the shape looks like. Because we're going to talk about some really complex things on that.